A hurricane of unimaginable scale endlessly circles our neighboring world. This is the atmospheric super-rotation of Venus, a phenomenon where the planet's entire sky moves 50 times faster than the planet itself. By the end of this journey, you will understand 25 of the deepest mysteries locked within this alien weather system. We will explore what powers this global tempest and investigate the strange, stationary patterns etched into its clouds. When you think of a hostile planet, what single image defines it for you? The entire sky of Venus is in motion, a global river of gas flowing at hurricane speeds. Yet the planet itself turns at a crawl. This is the central puzzle, the first and greatest mystery. What force could possibly drive this atmospheric engine, keeping it spinning so much faster than the world below? On Earth, our weather is powered by the sun heating the oceans and land, creating rising air and pressure differences. Venus presents a stark contrast. Its surface is a landscape of perpetual twilight, shielded from direct sunlight by a global blanket of clouds. There are no vast oceans to store and release heat energy. So what is the power source? The primary suspect is the sun itself, but in a different way than you might think. Scientists call this a thermal tide. As sunlight heats the upper atmosphere, it does not do so evenly. This creates a massive planet-wide wave of pressure and temperature that pushes on the atmosphere, potentially giving it a continuous shove. Another theory suggests the planet's incredibly slow rotation might be the key. The sluggish spin of the solid planet could allow momentum to be transferred upward into the faster-moving atmosphere, like a child pushing off a slow-moving merry-go-round to spin faster. The debate is far from settled. Could the energy come from the planet's scorching hot interior, rising through volcanic vents? Or is it a complex and unknown interplay of solar heating and planetary dynamics? We simply do not have a definitive answer. This fundamental question of what fuels the storm is the key that could unlock all the other secrets of this alien world. Our planet is wrapped in a powerful magnetic shield, a force field that deflects the sun's constant stream of charged particles. Venus has no such protection. This lack of a global magnetic dynamo is the second great mystery, and it fundamentally changes how the solar wind interacts with the world. Without a magnetic field to push it away, the full force of the solar wind slams directly into the planet's upper atmosphere. Think of it like standing in a gentle breeze on Earth versus standing in the direct blast of a sandblaster on Venus. This brutal interaction does more than just erode the atmosphere over eons. Scientists are now asking a startling question. Could this direct assault by the solar wind actually be helping to drive the super-rotation itself? The constant buffeting might be transferring energy and momentum into the upper layers of the air, giving the already fast-moving clouds an extra push. Spacecraft like Venus Express have watched as particles from the atmosphere are torn away, forming a long, comet-like tail stretching far into space. This steady loss is a puzzle in itself, but the energy exchange is the real enigma. Does the solar wind act like a cosmic hand, spinning the top of the atmosphere? Or does the absence of a magnetic field allow for a more direct and chaotic form of energy transfer, one that our own protected Earth cannot show us? We are left to wonder if the very thing that makes Venus so hostile, its exposed atmosphere, is also the secret engine behind its greatest atmospheric spectacle. As we move from the planet's sun-scorched equator towards its poles, the super-rotation reveals another layer of its strangeness. High above the north and south poles of Venus, the atmosphere does not simply slow down. It collapses into a monstrous, swirling structure known as the polar vortex. This is not one, but two distinct vortices stacked on top of each other, a double-eyed storm of unimaginable scale. The Venus Express spacecraft watched in awe as this feature, dubbed the cold collar for its frigid temperatures, morphed and changed shape from a single dipolar swirl to an almost perfect circle, and then into a squashed, irregular oval. This shape-shifting behavior is a mystery in itself. Why does this atmospheric giant constantly change its form? On Earth, our polar vortices are fragile things, breaking apart and reforming with the seasons. The vortex on Venus is a permanent and terrifyingly stable fixture, a whirlpool wider than our entire planet that has likely been spinning for millions of years. Its immense stability suggests it plays a critical role in the global weather machine. Scientists believe these polar vortices may act as colossal energy sinks. Imagine the super-rotating winds as a river flowing from the equator. As this river of air travels poleward, it carries with it immense heat and momentum. When it reaches the pole, all that energy has to go somewhere. It gets funneled into these vortices, which churn and dissipate it in ways we do not fully understand. This creates a profound feedback loop. The super-rotation feeds the vortex, and the vortex, in turn, may help regulate the speed of the super-rotation by acting as a planetary pressure release valve. We are only beginning to comprehend this self-sustaining atmospheric dance, where the storm itself creates the conditions that keep the storm alive. Descending from the polar vortex, we plunge into the thick, sulfuric haze of the main cloud decks. Here we encounter a paradox that defies all earthly intuition. At the very top of the clouds, some 60 to 70 kilometers high, the wind screams past at over 360 kilometers per hour. Yet on the surface below, the air is almost perfectly still. You could stand in that crushing 900-degree heat and feel barely a whisper of a breeze. This is the fourth mystery, the cloud-level conundrum. How can a planet have a virtually calm surface and a supersonic sky just a short distance above it? This creates a vertical canyon of wind shear, a gradient of speed so extreme it should, by all our models, tear itself apart through turbulence, but on Venus it persists. The atmosphere is not a single, uniform layer. It is a structured world of its own, with multiple decks of clouds made mostly of sulfuric acid droplets. These clouds are not just passive observers, they are active players, likely engines in this global storm. The upper clouds are dark, absorbing a tremendous amount of the sun's energy. This creates a stark temperature difference, with the cloud tops being far hotter than the layers below or above. It is this differential heating, this solar power absorbed directly into the cloud layer, that may provide the constant push the fast winds need. The chemistry itself adds another layer of complexity. The perpetual creation and destruction of sulfuric acid droplets releases heat in a complex cycle, potentially adding more energy into the atmospheric engine. The data paints a clear and puzzling picture. Wind speeds do not just jump from calm to hurricane force. They increase steadily with altitude, a smooth acceleration that points to momentum being transferred from the top down. This vertical profile is the exact opposite of what we see on Earth, where surface friction slows the wind. Something hidden within those yellow cloud decks is actively driving this acceleration, a process we have not yet been able to replicate in our most advanced computer simulations. The clouds of Venus are not just a veil hiding the planet, they are the beating heart of the storm, and we are only just beginning to understand their rhythm. Yet within that hurricane of motion, there are features that stand perfectly still. Etched across the planet's face are colossal, dark shapes, a giant horizontal Y and other wave-like patterns scientists call psi. These are not clouds moving with the wind. They are fixed in place, locked to the sun as the planet and its atmosphere whirl madly beneath them. Imagine a river flowing at breakneck speed, and on its surface, a leaf that does not move downstream but remains pinned to a single spot. That is the paradox these patterns present. Since the Mariner 10 spacecraft first saw them, these stationary waves have been a source of deep confusion. How can anything remain motionless in an atmosphere that screams past at hundreds of kilometers per hour? One compelling theory points to the ground far below. Venus has towering mountains, and as the super-rotating winds slam into these massive obstacles, they could be forced upward, creating ripples in the air known as gravity waves. These waves would then travel vertically through the thick atmosphere until they reach the cloud tops, where they manifest as these fixed, dark shapes. It is as if the ghost of the surface topography is being projected onto the sky. Another idea points to the sun's relentless heating. The thermal tide, that global wave of pressure we discussed earlier, might be creating standing waves in the atmosphere, much like the stationary vibrations you can create in a rope by shaking it at just the right frequency. These solar-driven waves would naturally be fixed relative to the sun, creating the permanent patterns we observe. These enigmatic features are far more than just curious markings. They are likely critical control points in the global weather system. By acting as obstacles or channels in the atmospheric flow, they could be transferring energy and momentum between different layers of the wind, helping to maintain the very super rotation they so defiantly resist. To understand the storm, we must first understand its unmoving anchors. These stationary waves are more than just surface ghosts. They hint at an invisible engine churning deep within the atmosphere, an engine powered by gravity waves. Forget the cosmic ripples of black holes. On Venus, gravity waves are a far more local phenomenon, a fundamental pulse of a fluid world. Imagine tossing a stone into a perfectly still pond. The ripples that spread outward are a perfect analogy. They are waves of buoyancy where a parcel of air is pushed upward and then gravity pulls it back down, creating an oscillation that can travel vast distances. On Venus, the stones are its colossal mountain ranges, and the pond is its incredibly dense, deep atmosphere. As the super-rotating winds slam into a towering peak like Maxwell Montes, the air is forced to rise. It then sinks back down, but the immense density of the atmosphere allows this rocking motion, this wave, to travel vertically for dozens of kilometers. These are not small ripples, they are planet-scale undulations carrying immense energy from the surface toward the sky. The true mystery unfolds where these waves break. High in the upper atmosphere, where the air grows thinner, these giant waves crest and collapse, much like an ocean wave crashing onto a shore. It is in this violent breaking process that they are thought to perform their crucial task, dumping their momentum directly into the super-rotating winds. It is a continuous planet-wide pump, where the slow grind of wind over mountains injects energy into the hurricane above. Proving this is the monumental challenge. We cannot see these waves directly through the permanent cloud cover. Scientists must become atmospheric detectives searching for their fingerprints. They look for subtle, periodic changes in temperature and brightness in the cloud tops, the telltale signs of a wave having reached the surface of the visible sky. Complex computer models suggest this transfer is vital, that without this constant pumping from below, the super-rotation might slowly bleed its speed and fade. Yet we are left with a profound question. Is this gravitational pumping the primary driver, or just one vital component in a machine we have only begun to map? The planet keeps the true power of its hidden pulses a closely guarded secret. This thermal tide is a planetary heartbeat driven directly by the sun. As the star's radiation strikes the day side of Venus, it heats the upper atmosphere, causing the air to expand and creating a colossal, invisible bulge of high pressure. On the frigid night side, the opposite occurs. The air cools, contracts, and sinks. This daily cycle of heating and cooling generates a planet-wide wave that relentlessly pushes the atmosphere in the direction of the super-rotation, effectively giving it a continuous shove. The real magic lies in the transfer of momentum. As this thermal tide pushes on the atmosphere, it is thought to draw a tiny amount of angular momentum, a measure of spin from the planet's own sluggish rotation. It is a cosmic transaction where the sun's energy helps the atmosphere steal a little spin from the solid ground below, accelerating the winds to their incredible speeds. Yet this creates a profound puzzle. Earth experiences thermal tides as well, but their effect is trivial, lost in the chaos of our weather systems driven by ocean currents and landforms. Why is this process so extraordinarily effective on Venus? The planet's incredibly slow rotation is a key suspect. A single Venusian day lasts longer than its entire year, meaning the dayside is baked for months on end. This allows the thermal tide to build up to an immense strength, becoming the dominant force in the upper atmosphere. Furthermore, the lack of oceans and a relatively smooth surface means there is little to disrupt this global wave as it travels. But even with these advantages, our most sophisticated computer models hit a wall. When scientists program all the known physics of this solar pushing, the simulated winds never quite reach the 360 km/h fury we observe. Something is missing from the equation. Complicating the picture is the sun's gravitational pull. While the moon's gravity creates ocean tides on Earth, the sun's gravitational tide on the atmosphere of Venus is minuscule, far too weak to account for the phenomenon. This confirms that the heat-driven thermal tide is the true engine, but it is an engine we do not fully understand. The models struggle, leaving us with a critical gap in our knowledge. Is there an amplifier we have not yet discovered within those acidic clouds, or does the thermal tide work in concert with another, hidden mechanism to achieve such violent winds? The Sun gives the atmosphere its push, but Venus adds a mysterious thrust of its own. The very existence of this global hurricane depends on a single, invisible currency, the currency of spin. This is the mystery of atmospheric angular momentum. In simple terms, angular momentum is the property that keeps a spinning object spinning. A figure skater pulls her arms in to spin faster, conserving that momentum in a tighter circle. For a planet, the total amount of angular momentum is a fixed value, a cosmic budget that cannot be created or destroyed, only transferred. This is where Venus presents a profound physical anomaly. The planet itself rotates with a painfully slow spin, meaning its solid body possesses very little angular momentum. Yet its atmosphere, a massive whirling shell of gas, holds a staggering amount. The atmosphere spins 50 times faster than the planet below. How did it acquire this colossal reserve of spin, and how does it hold onto it against the constant, grinding friction of the planet's surface? The conservation law tells us this momentum had to come from somewhere. It was not created out of nothing. One possibility is that the atmosphere has always possessed this spin, a relic from the planet's formation billions of years ago, a primordial rotation that the solid planet somehow lost. Another, more dramatic theory suggests a colossal impact. In the solar system's violent youth, a massive object could have slammed into Venus, imparting a tremendous amount of angular momentum directly to its atmosphere, a spin-up event from which it has never recovered. The planet's slow, backward rotation could even be a scar from such a cataclysm. Yet the mystery deepens when we consider the present day. The surface of Venus is not smooth glass, it is a landscape of mountains and valleys. As the super-rotating winds flow over this rough terrain, they should experience friction, a constant drag that would steadily bleed momentum away from the atmosphere and slow the winds down. But they do not slow down. This means there must be a continuous, planet-wide mechanism that is pumping momentum back into the atmospheric engine, replenishing what is lost to friction. The thermal tide from the Sun is one candidate for this pump, and the breaking gravity waves from the mountains might be another. The atmosphere is not just a passive holder of this momentum, it is an active manager, constantly balancing its cosmic budget of spin against the losses from the surface below. We are left staring at a slowly turning world wrapped in a screaming gale, a system that by all rights should have ground to a halt eons ago. The very persistence of the storm is a testament to a hidden, self-sustaining cycle we are only beginning to perceive. At the planet's searing equator, the superrotation reaches its peak velocity, a screaming river of gas we might call an equatorial jet stream. But this is no smooth, laminar flow. Hidden within this fastest part of the global hurricane are complex, swirling eddies and pulsing waves, features that should, in theory, destabilize the entire system. Yet they do not. This is the core of the ninth mystery, the paradox of the stable jet. On Earth, our jet streams are meandering ribbons of wind, constantly shifting, buckling, and breaking apart into storms. They are inherently chaotic. The jet on Venus is remarkably robust, a steady, high-speed lane that has persisted for decades of observation. Why does this engine of the superrotation not tear itself to pieces? The answer may lie within those very eddies. Scientists now suspect these smaller swirls are not agents of chaos but essential cogs in the machine. They could be transferring energy and momentum from the smaller scales of turbulence up to the larger, global scale of the superrotation, actually reinforcing the jet stream instead of breaking it down. It is a counterintuitive idea where local instability creates global stability. This process is deeply intertwined with another planetary cycle, the Hadley circulation. Imagine a colossal vertical loop of moving air. At the equator, superheated air rises violently upward. Once it reaches the cloud tops, it begins a high-altitude journey toward the poles. There it cools, sinks, and flows back toward the equator at lower altitudes, completing the loop. This is the planet's primary heat distribution system, and it is here that the mystery deepens. How does this vertical loop interact with the horizontal, super-rotating winds? The two systems are locked in a continuous dance. The rising air at the equator may be injecting momentum directly into the base of the jet stream, acting like a constant accelerator. Conversely, the poleward flow of the upper branch of the Hadley cell could be helping to maintain the sharp speed gradient of the superrotation by carrying slower moving air away from the equator. The system may be a self-regulating engine where the superrotation influences the heat transport, and the heat transport, in turn, sustains the superrotation. We are left to ponder a global weather machine of breathtaking complexity, where every part is connected and every swirling eddy might hold a secret to the storm's enduring power. While the sunlit side of Venus blazes with energy, the planet's night side is a realm of perpetual and profound darkness. Here, the sun has not risen for months, and the temperature plummets hundreds of degrees. This is the stage for the 10th mystery, a place where the rules seem to break. The superrotation does not stop at the terminator, the line dividing day from night. The hurricane force winds scream on, unabated, into the cold and the black. What force could possibly keep this atmospheric river flowing at full speed, long after its primary engine, the sun, has vanished from the sky? The answer lies in the atmosphere's incredible ability to transport heat. Think of the dayside atmosphere as a colossal thermal battery. It soaks up immense solar energy, and the super-rotating winds themselves act as a global delivery system, a high-speed conveyor belt that rushes this stored heat from the day side to the night side. This is not a gentle transfer, it is a planetary-scale flood of energy, working to balance the extreme temperatures and maintain the atmospheric pressure differences that drive the winds. Yet even this explanation is incomplete. The night side reveals its own bizarre phenomena that defy simple logic. Spacecraft have observed the clouds here becoming irregular and strangely patchy, as if the very structure of the atmosphere unravels in the darkness. More mysteriously, the night sky of Venus sometimes glows with a faint, ethereal light, a phenomenon called airglow. This is caused by complex chemical reactions as atoms and molecules, energized on the day side and carried by the winds, recombine and release their stored energy as a soft luminescence. This glowing is a ghostly signature of the hidden processes at work. The fundamental puzzle remains. Our best computer models of weather rely heavily on solar heating as the primary driver for circulation. On the night side of Venus, that driver is gone. The winds persist through sheer momentum and the transport of heat, but something more must be happening to counteract the constant drag and friction that should be slowing the air down. Could there be a secondary, hidden engine churning in the darkness, perhaps driven by the violent churn of the polar vortex or by the relentless release of heat from the planet's own interior through vast, unseen volcanic systems? The night side of Venus is a stark reminder that our understanding of this world is still half in shadow, a cold and dark frontier where the super-rotation whispers its most challenging secrets. This unrelenting hurricane raises a deeper question about time itself. How permanent is this atmospheric state? Is the super-rotation a fleeting chapter in Venus's long history, or has this global storm raged for millions, even billions of years? The 11th mystery confronts the storm's stability across geological time. Our direct observations span only a few decades, a mere blink of an eye on a planetary scale. Yet within that short window, the data holds tantalizing clues. Measurements from the Pioneer Venus orbiter in the 1980s, compared with those from the Venus Express mission decades later, suggest the wind speeds might not be perfectly constant. They appear to pulse, sometimes faster, sometimes slower, by tens of kilometers per hour. This subtle variation hints at a system with its own rhythms, a heartbeat of acceleration and deceleration we do not yet understand. The core phenomenon, however, has never faltered. Every time we look, the clouds are racing. This incredible persistence is a puzzle in its own right. The atmosphere is constantly losing energy. Friction with the surface, the radiation of heat into space, and the internal churning of turbulence all act as brakes, trying to slow the winds down. For the super-rotation to remain stable, there must be a perfect planet-wide balance between the energy being lost and the energy being pumped back in. This suggests the existence of powerful negative feedback mechanisms. Think of it like a thermostat for a hurricane. If the winds were to speed up too much, perhaps the increased turbulence would enhance the mixing of air, which in turn would dissipate heat more efficiently and rob the system of its driving energy, slowing it back down. Conversely, if the winds slowed, the reduced mixing might allow heat to build up, strengthening the thermal tide and giving the atmosphere a stronger push. The system may be a self-correcting engine, constantly fine-tuning its own fury. The most profound question is what would happen if this balance were ever truly broken. If the super-rotation were to suddenly stop, the consequences would be catastrophic for the Venus we know. The high-speed winds are what distribute the sun's heat evenly from the day side to the night side. Without that conveyor belt, the day side would grow unimaginably hotter, while the night side would plunge into a deep, permanent freeze. The planet's relatively uniform surface temperature would shatter into extremes. Such a climate collapse would leave its mark, perhaps in strange geological formations or mineral deposits that future landers could one day find. The very fact that this has not happened tells us that the super-rotation is a robust, deeply integrated feature of Venus. It is not a temporary weather pattern. It is the defining state of the planet's climate, a storm that has likely shaped the world for eons, and one that will likely continue its endless scream long into the future. The dark markings that swirl across the face of Venus are more than just patterns. They are a chemical signature, a clue to one of the planet's most stubborn secrets. These are the stains of an unknown ultraviolet absorber, a mysterious substance embedded within the sulfuric acid clouds that voraciously eats the sun's high-energy light. We have watched these dark features for decades, yet we still have no idea what this substance actually is. Its identity remains one of the greatest chemical mysteries in our solar system. The list of suspects is long and exotic. It could be a strange form of elemental sulfur, a sulfur allotrope created by complex reactions high in the atmosphere. Other theories point to ferric chloride, a compound that could exist in those acidic conditions, or even a form of microscopic life floating in the temperate cloud layers. Each candidate has its own problems, and none perfectly match the unique way this absorber darkens and lightens over time. This is not just an academic puzzle. The identity of this absorber is critical because it is a master of energy. It is the primary agent that controls how solar power is distributed within the upper atmosphere. The dark regions where it concentrates absorb vast amounts of sunlight, becoming intense local hotspots. The brighter, reflective clouds surrounding them remain significantly cooler. This creates a dramatic patchwork of temperature and pressure across the planet's face. It is this very patchwork that may be the hidden hand guiding the super-rotation. Think of it like a giant planetary scale engine. The hotspots created by the absorber act like pistons, creating zones of rising air. The cooler areas are where the air sinks. This constant churning motion, driven directly by the uneven absorption of sunlight, generates powerful pressure gradients. The atmosphere, seeking balance, rushes from high pressure to low pressure areas, and this relentless push is precisely what helps maintain the hurricane force winds of the super-rotation. The unknown chemical is not just a passenger in the storm. It is likely a chief engineer, its distribution and properties directly influencing the strength and stability of the entire global wind system. The hunt to name this compound is therefore far more than a chemistry experiment. It is a quest to find the fundamental link between the sun's raw energy and the atmospheric fury it creates, a vital piece without which the machine of Venus will never fully make sense. That same global wind system may hold the key to the planet's most infamous feature, its hellish surface temperature. The super-rotation and the runaway greenhouse effect are locked in a profound and unresolved embrace, a chicken and egg mystery of planetary proportions. The winds act as a colossal heat distribution network, relentlessly carrying the blistering heat from the day side across to the frigid night side. This prevents the dark side from cooling down drastically and, in turn, stops the day side from overheating even further. By smoothing out these extremes, the super-rotation helps maintain the planet's globally uniform oven-like temperature of 465 degrees Celsius. But which came first? Did the super-rotation arise as a consequence of the runaway greenhouse, a necessary response to the incredible heat, or was it the other way around? Could a primordial version of these fast winds have been a catalyst, efficiently moving solar heat around the young planet and inadvertently pushing its climate over the edge into a permanent greenhouse state? This feedback loop is a planetary trap. The heat drives the winds, and the winds enforce the heat, creating a self-perpetuating cycle from which there is no escape. For scientists studying climate, this is more than a puzzle about our neighbor. It is a stark and sobering lesson. Venus shows us that an atmosphere is not just a blanket, it is a dynamic global engine. Changes in its circulation can have irreversible consequences, locking a world into a hostile state for eons. Understanding this link is not just about decoding Venus' past. It is about comprehending the delicate and powerful forces that govern any planet's climate, including our own. Beneath the churning yellow clouds, the character of Venus changes completely. We plunge into a deep ocean of air, a lower atmosphere so dense and sluggish it forms what scientists call a stagnant lid. This region, extending down to the surface, is a world of profound calm, a stark contrast to the hurricane raging just dozens of kilometers overhead. The air here is not a gentle breeze, it is a syrupy, supercritical fluid, so thick that it behaves more like a liquid than a gas. Measuring conditions in this oppressive realm is a monumental challenge. Probes that have descended into this layer survive for mere minutes before being crushed and melted, giving us only fleeting, fragmented snapshots of its nature. The central puzzle of this stagnant lid is its apparent disconnection from the frenzy above. How can momentum, the very essence of the super-rotation spin, possibly be transferred upward through this seemingly motionless layer? It is like trying to spin the top of a swimming pool by gently stirring the very bottom. The forces involved seem utterly mismatched. the answer may lie in processes we can barely observe. While the large-scale flow is stagnant, the lower atmosphere might be seething with small-scale convection and subtle turbulence. Imagine a pot of water on a low simmer. The surface might look almost still, but just beneath, tiny bubbles of hotter water are constantly rising, creating a faint, churning motion. On Venus, the scorching surface, heated to over 460 degrees Celsius, could be generating similar, weak thermal plumes. These pockets of rising hot air would carry with them a tiny amount of momentum as they ascend. Individually, each plume is insignificant, but collectively, across the entire globe, this constant, faint churning could act as a planet-wide pump, slowly but relentlessly feeding momentum upward from the ground toward the cloud bases. This hidden turbulence could be the vital bridge, the missing link that connects the planet's hot surface to the engine of the super-rotation high above. The stagnant lid, then, is not a true lid at all. It is a deceptive layer of calm, masking a subtle, global transfer of energy that fuels the greatest storm we know. Unlocking the secrets of this deep, quiet ocean may finally reveal how the planet's very heat gives birth to the fury in its sky. This planetary engine may be rooted deep in the very ground of Venus. The colossal mountain range of Maxwell Montes rises higher than Mount Everest, a titan of rock standing against a sky of supercritical air. The mystery here is whether these immense surface features can punch through the planet's dense, insulating lower atmosphere and directly influence the hurricane raging far above. As the global winds sweep across these vast highlands, they do not simply flow over them. They are forced to rise, creating immense, invisible ripples in the atmospheric ocean known as mountain waves. These are not the gravity waves of cosmic events, but powerful, localized pulses of buoyancy, like the standing waves that form in a river downstream of a massive boulder. The question is whether these terrestrial ripples can travel all the way up to the cloud tops, over 60 kilometers high. Data from the Magellan spacecraft, which mapped the surface through the clouds with radar, offers a tantalizing clue. The mission revealed a surprising correlation. The cloud patterns observed from orbit often show distinct, wave-like formations that align almost perfectly with the massive highland regions below, as if the ghost of the mountains is being projected onto the underside of the cloud deck. This suggests a direct, vertical connection that defies our intuition about a fluid layer so thick and sluggish it was thought to be a stagnant lid. How can a surface feature possibly make its presence known so high up? The sheer scale of Venus provides the answer. The atmosphere is not just thick, it is incredibly deep and massive. A mountain wave generated by a range the size of Maxwell Montes would not be a small ripple. It would be a planetary-scale undulation carrying immense energy upward. The dense air actually helps propagate these waves over vast vertical distances, allowing them to travel from the surface toward the cloud bases without dissipating completely. When these mountain waves finally reach the upper cloud layers where the air is thinner, they are thought to break, much like an ocean wave crashing on a shore. It is in this violent, collapsing process that they may dump their momentum directly into the super-rotating winds, giving them a continuous push. This would make the surface topography an active participant in the storm, a hidden pump that uses the slow grind of wind over rock to fuel the atmospheric frenzy above. Yet the evidence remains circumstantial, a correlation seen from orbit that we cannot yet confirm from within the maelstrom. Are these mountain waves a primary driver of the super-rotation, or merely a contributing whisper in a chorus of forces? The silent, brooding mountains hold the answer, their influence potentially written across the sky in a language of waves we are only just learning to read. This endless hurricane might seem like a perfect, unchanging machine, but is it truly constant? The 16th mystery pulls back the curtain on time itself, questioning whether the super-rotation has its own hidden rhythms. We have watched the clouds race for decades, yet the data tells a conflicted story. Some observation periods show the wind speeds holding a steady, terrifying velocity. Other datasets reveal subtle pulses, with the global winds speeding up or slowing down by tens of kilometers per hour over months or years. The central question is whether we are witnessing real planetary variability or merely the limitations of our own vision, peering through that thick veil of clouds. Detecting a true daily cycle is a monumental challenge. A single day on Venus lasts longer than an entire year, meaning the sun bakes the atmosphere for months on end. This slow rotation should smear out any distinct day-night pattern in the winds, yet some scientists speculate that the relentless thermal tide could still imprint a faint daily heartbeat on the system, a pulse we have not yet been able to feel. The concept of seasons on Venus is even more alien. With an axial tilt of less than 3 degrees, the planet has no summer or winter as we know them. Its seasons are dictated solely by its slightly eccentric orbit, bringing it closer to and farther from the Sun over the course of its year. This variation in solar heating is small, but in a system as finely tuned as the super-rotation, even a small change in energy input could theoretically cause a noticeable response. The debate is fierce. Are these observed fluctuations in wind speed a sign of the super-rotation's inherent dynamic nature, a system that breathes and adjusts like a living thing? Or are they simply ghosts in the data, caused by the difficulty of tracking the same cloud features from different spacecraft across different instruments over many years? This is not just an academic argument. If the winds truly vary, it means the super-rotation is a more delicate and complex engine than we thought, sensitive to subtle changes in solar power or internal dynamics. Its stability would not be a given, but a precarious balance, constantly corrected by feedback loops we have yet to map. The possibility of real variability opens a door to a deeper understanding, suggesting that even this global hurricane has its seasons, its years of relative calm and periods of heightened fury, all playing out on a timescale we are only beginning to perceive. Even the most basic fact about this storm, the speed of its rotation, has been a source of confusion for centuries. Early astronomers peering through telescopes saw vague, shifting markings in the clouds of Venus. They calculated a 4-day rotation period for the planet, a figure that seemed reasonable for a world so similar in size to our own. This was the first flawed measurement of the super-rotation, a misunderstanding that would persist for generations. The truth was far stranger. The planet itself was not spinning in 4 days, it was the atmosphere that was. The solid ground below took 243 Earth days to complete a single, sluggish turn. The discrepancy between the observed cloud motion and the planet's actual rotation was the first clue to the atmospheric madness, but it was a clue misinterpreted for decades. The confusion only deepened with the arrival of the space age. Different probes armed with different instruments began to report conflicting data. One mission would clock the cloud-top winds at one speed, while another, just a few years later, would find them noticeably faster or slower. For a time, it was impossible to say for certain if we were looking at a steady gale or a variable hurricane. Were these discrepancies simply ghosts in the machine, the limitations of older technology? Tracking a faint, shifting cloud feature from millions of kilometers away is an immense challenge. Early missions had lower resolution cameras and less sophisticated ways of following the same atmospheric parcel as it moved. A slight error in identification could lead to a large error in calculated wind speed. Or was the atmosphere itself playing tricks on us? The cloud decks are a fluid, dynamic ocean with features that form, merge, and dissipate constantly. Trying to pin down a single, definitive rotation period for such a system is like trying to measure the exact speed of a river by timing a single bubble. The bubble may pop or be caught in a small eddy, giving a reading that does not represent the river's true, powerful current. This historical puzzle forces a humbling realization. Even after decades of observation, one of the most fundamental parameters of the super-rotation, its exact and constant speed, has been frustratingly difficult to pin down with absolute certainty. This lingering uncertainty over a simple number reminds us that we are not studying a static picture, but a living, breathing, and deeply complex atmospheric beast. Within the grand river of the superrotation, a hidden chaos churns. This is the world of turbulence and eddies, the 18th mystery, where small-scale disorder may be the very source of the global order we observe. Picture the jet stream not as a smooth ribbon, but as a river filled with countless whirlpools and swirls, some no larger than a few kilometers across. On Earth, such features are often agents of disruption, breaking down larger weather systems. On Venus, they may play the opposite role. Scientists suspect these tiny, chaotic motions are secretly feeding the superrotation. The process is known as an inverse energy cascade. Instead of large flows breaking down into smaller eddies, the smaller eddies merge and organize, transferring their energy and momentum upward to fuel the planet-wide river of wind. It is as if a million tiny motors were all working in concert to push a single, colossal turbine. This creates a profound paradox where local instability creates global stability. The challenge for scientists is that these vital, small-scale processes are almost impossible to capture in global climate models. The computing power required to simulate every tiny eddy across an entire planet is beyond our reach. Instead, modelers must use approximations, formulas that guess at the net effect of all that sub-grid scale turbulence. Get this detail wrong, and the entire simulation falls apart. Some models with one set of approximations fail to produce any superrotation at all. The simulated winds remain sluggish and Earth-like. Other models with slightly different turbulence parameters might produce winds, but they are pathetically weak, a mere breeze compared to the observed hurricane. The most frustrating outcomes are models that overshoot, generating atmospheric currents far more violent than anything we see. This delicate balance tells us that the superrotation is not just a simple consequence of solar heating. It is an emergent phenomenon, a precise dance between the massive push of the thermal tide and the trillions of tiny pushes from unseen eddies. We are left to wonder if the true secret to the storm's endurance is written in a language of chaos we are only beginning to translate, a hidden turbulence that sustains the very wind it seems to threaten. The planet's own slow, backwards rotation is a cosmic anomaly in itself. Venus spins in the opposite direction to most planets, a sluggish retrograde whirl that takes longer than its entire year to complete. This bizarre behavior is the 19th mystery, and it may be the ultimate key to understanding the atmospheric frenzy above. The leading theory points to a cataclysm in the solar system's violent youth. A colossal impact, perhaps with a protoplanet the size of Mars, could have slammed into a young, faster-spinning Venus. The titanic collision might have delivered a glancing blow so immense that it literally stopped the planet's original spin and sent it spinning backwards, while also stripping away any moons it might have possessed. This same apocalyptic event could have directly seeded the conditions for the superrotation. The impact would have transferred a staggering amount of energy and angular momentum directly into the planet's early atmosphere, giving it a ferocious initial spin that the planet's solid body, now crippled and slow, could never match. The collision could have vaporized oceans and triggered the runaway greenhouse effect, creating the thick, dense atmosphere we see today. The connection between the planet's slow roll and its fast sky is a complex gravitational and thermal dance. The slow rotation allows the sun's thermal tide to build up to immense strength, giving the atmosphere a powerful, continuous push. Conversely, the super-rotating atmosphere itself exerts a tiny but constant gravitational and frictional tug on the planet's surface. This raises a profound question. Is the super-rotation merely a consequence of the slow spin, a product of that ancient violence, or has the endless hurricane over billions of years acted as a brake, its constant drag helping to maintain the planet's sluggish pace? They may be locked in a feedback loop, a planetary state where the slow spin enables the fast winds, and the fast winds help enforce the slow spin. This intertwined fate suggests that the storm in the sky and the crawl of the ground are not separate puzzles, but two halves of a single, enduring mystery written in the aftermath of a forgotten cosmic crash. But could this endless storm be fighting back against the world that birthed it? The planet's slow spin may have enabled the superrotation, but the superrotation itself may be returning the favor, exerting a subtle cosmic drag on the solid ground below. This is a mystery of a two-way street where the atmosphere is not just a passenger, but an active force shaping the planet's very rotation over geological time. The physics hinges on friction and pressure. Imagine resting your hand on a spinning merry-go-round. Your hand slows it down through friction. Now, imagine the super-rotating atmosphere as a colossal, fast-moving hand, constantly brushing against the mountain ranges and vast plains of Venus. This contact creates a tiny but relentless torque, a twisting force that acts to either slow the planet down further or, in some complex scenarios, speed it up. The transfer of angular momentum through this contact is incredibly difficult to quantify. The atmosphere is not a solid shell, it is a turbulent fluid sloshing against a rough, complex surface. Furthermore, the immense atmospheric pressure, 90 times that of Earth, means that the air does not just flow over mountains, it rams into them with phenomenal force, creating pressure differences on the windward and leeward sides that can also impart a net push or pull on the planet's crust. Could the collective drag of 1 trillion such interactions over millions of years be measurably altering the length of a Venusian day? Our current models and measurements are not precise enough to give a definitive answer. Detecting a change in a rotation period that is already 243 Earth days by a few seconds over a century is a monumental challenge from Earth or orbit. This presents a profound feedback loop of epic proportions. The planet's slow rotation allows the thermal tide to push the atmosphere into a frenzy, and that frenzied atmosphere, in turn, may be applying a brake, helping to keep the planet's spin locked in its slow, backwards crawl. The storm and the world are not separate entities. They are locked in a gravitational embrace, a dance of push and pull that has likely been ongoing for eons, each partner subtly shaping the destiny of the other in a cycle we are only beginning to perceive. Venus is not alone in its atmospheric defiance. Far out in the cold depths of the solar system, another world performs a similar, impossible dance. Saturn's largest moon, Titan, wrapped in a thick orange haze, also has an atmosphere that races around the moon faster than the moon itself rotates. This discovery transforms the mystery from a solitary oddity into a cosmic pattern. Why do these two wildly different worlds both host a super-rotating sky? Titan is a frozen realm of methane lakes and water ice, 1 billion kilometers from the Sun. Its atmosphere is thick but far less massive than the crushing air of Venus. It receives only a tiny fraction of the solar energy that bathes our neighboring planet. Venus, by contrast, is a scorching, high-pressure hellscape drowning in sunlight. If the same phenomenon can occur under such opposite conditions, what universal rule is at play? The answer seems to lie not in the specifics of heat or pressure, but in the fundamental mechanics of how an atmosphere moves energy. Both Venus and Titan have atmospheres that are deep and coupled to their surfaces, yet their high-altitude winds are somehow decoupled, free to accelerate to incredible speeds. The key may be a process that efficiently takes energy from the Sun, or perhaps from the planet's own rotation, and pumps it directly into the atmospheric winds, bypassing the drag of the ground below. On Titan, the driving force might be tidal forces from Saturn's immense gravity, or complex interactions between its methane cycle and the weak sunlight. On Venus, it is the powerful thermal tide. The common thread is the existence of a continuous, planet-wide push that can overcome surface friction. This comparative view reveals that superrotation is not a freak event. It is a possible state for any planetary atmosphere with the right combination of depth, energy input, and fluid dynamics. Earth, with its patchy oceans and rugged continents, lacks the smooth, global consistency needed for such a unified flow. Mars, with its thin, anemic air, does not have enough atmospheric substance to sustain it. Venus and Titan show us the boundaries. They are the two data points that define the edges of this atmospheric rulebook. By studying their contrasts, we begin to understand the universal recipe for a world whose sky outruns its ground. The enigma of Venus is no longer just about one planet's strange weather. It is a vital clue in our quest to predict what the skies of distant exoplanets might be like, helping us to classify the types of storms that could rage on worlds we have not yet even seen. This frustrating reality is the 22nd mystery, a puzzle born from absence. For every answer our robotic explorers have sent back, they have left behind two more profound questions, creating a legacy of gaps in our knowledge. The pioneering Soviet Venera landers gave us our first and only grainy photographs from the hellish surface, surviving for mere minutes in the crushing heat. They confirmed the extreme conditions but could tell us almost nothing about the complex winds swirling just above. The American Pioneer Venus mission in the 1980s was an orbital orchestra, using multiple probes to build the first global snapshot of the atmosphere. It mapped cloud tops and tracked broad wind patterns, but its instruments were like a low-resolution camera trying to capture a hurricane's finest details. It saw the river, but not the trillions of swirling eddies within it. Then came Magellan in the early 90s, a radar magician that pierced the clouds to reveal a world of volcanoes and vast lava plains. It gave us the ghostly correlation between surface mountains and cloud patterns, but it was blind to the chemistry and the invisible waves connecting the ground to the sky. Each of these missions was a triumph, yet each was like a visitor arriving for a single day in a city with a 1,000-year history, catching only a fleeting glimpse of its true life. The gaps they left are vast, especially in the treacherous lower atmosphere, that stagnant lid where our data is thinnest and our understanding most incomplete. We have almost no continuous measurements of how wind speed and composition change from the clouds all the way down to the surface, a vertical profile that is absolutely critical to decoding the engine of the super-rotation. The European Space Agency's Venus Express and Japan's Akatsuki orbiter have been our modern eyes in the sky, revealing the dynamics of the polar vortex, the strange nightside airglow, and the subtle variability in wind speeds. They confirmed that the super-rotation is a living, breathing system, not a static painting. Yet in doing so, they raised a host of new riddles. Why do the winds sometimes pulse? What causes the dark, ultraviolet markings to constantly shift and change? The better our instruments become, the more complex the mystery appears. We are now at a precipice, armed with decades of tantalizing clues but lacking the sophisticated tools needed for a final investigation. The path forward is clear. We need a new generation of missions, orbiters with advanced spectrometers to finally identify that unknown ultraviolet absorber, and balloons or long-lived aerial platforms that can ride the winds inside the cloud layer itself, measuring the vertical transfer of momentum and energy directly. We must go back to this world of endless storm, not for another glimpse, but for a long and detailed conversation with the sky itself. The silence surrounding Venus is about to be broken. After decades of waiting, a new armada of robotic explorers is being prepared for the journey, each one designed to pry a different secret from the world of endless storm. These are not mere orbiters, they are specialized detectives targeting the very heart of the super-rotation mystery. NASA Da Vinci+ mission is a daring atmospheric probe, a descent sphere that will plunge directly into the thick Venusian air. For just over an hour as it falls, its sophisticated instruments will taste the air, measure the winds, and analyze the chemistry from the cloud tops all the way down to the surface. This is our one chance to get a detailed vertical profile of the lower atmosphere, that stagnant lid we know so little about. It will hunt for the fingerprints of mountain waves and measure the elusive transfer of momentum, finally giving us a ground truth for what our models have only guessed. While Da Vinci Plus explores the sky, its sister mission, Veritas, will map the ground with a clarity we have not seen since Magellan. Its radar will pierce the clouds to reveal the surface in stunning high definition, mapping topography down to the scale of a few meters. This is not just for geological beauty. It will allow scientists to create the most accurate map yet of Venice mountains and valleys, and then directly correlate these features with the atmospheric wave patterns observed from above. Veritas will test the hypothesis that surface topography is an active driver of the superrotation, searching for the undeniable link between rock and sky. The European Space Agency's contribution, Envision, will act as the ultimate orbital observer. It will carry a suite of instruments to study both the atmosphere and the surface simultaneously, watching how they interact in real time. Its spectrometers will relentlessly scan the cloud decks, hunting for the chemical signature of the unknown ultraviolet absorber, hoping to finally put a name to the compound that helps power the storm. Together, these missions represent our most coordinated assault on the puzzles of Venus. They are built to find the missing pieces, to provide the hard data on vertical wind shear, momentum transfer, and surface atmosphere coupling that our current theories so desperately lack. Yet there is a humbling truth every planetary scientist knows. Every time we send a new mission to a world, we answer a handful of old questions and uncover a dozen new ones we were not even smart enough to ask. Da Vinci Plus might find a layer of unexpected chemistry in the lower atmosphere. Veritas could reveal a type of geological feature that alters our entire understanding of atmospheric waves. Envision might discover that the superrotation is even more variable and complex than we ever suspected. We send these robotic emissaries not to close the book on Venus, but to tear open the next chapter, one that will likely be filled with wonders and mysteries far stranger than we can currently conceive. The storm on Venus is more than a local curiosity, it is a universal key. As our telescopes discover thousands of worlds orbiting distant stars, a startling number appear to be Venus-like, rocky planets locked in a close, scorching embrace with their suns. These exoplanets present us with a fundamental challenge. We can measure their size and orbit, but what is the true nature of their climate? Is their surface a placid desert or a global hurricane? The answers lie in understanding atmospheric dynamics, and Venus is our only nearby model. The phenomenon of superrotation, if it is common on such worlds, would completely redefine their potential for life. An atmosphere that moves with such violence acts as a global temperature equalizer, preventing the kind of extreme temperature differences that could make one hemisphere molten and the other frozen solid. This might sound like a good thing, a stabilizer, but on Venus we see the terrifying flip side. This same circulation enforces a uniform, oven-hot temperature across the entire planet, efficiently distributing the star's brutal heat and likely helping to maintain the very runaway greenhouse effect that makes the world uninhabitable. So the critical question becomes, is a super-rotating atmosphere a prerequisite for a runaway greenhouse, or is it a consequence? The answer would create a new classification for planets. If we can confirm that Venus's thick atmosphere naturally develops this furious circulation, then we can predict that any similar exoplanet, any so-called hot Venus, likely possesses a permanent global hurricane in its sky. This single insight would tell us that their surfaces are not just hot, but are subjected to a specific and relentless form of weather, a climate state that profoundly impacts everything from geology to chemistry. Solving the mystery of what drives the storm next door gives us the decoder ring for interpreting the faint starlight filtering through the atmospheres of countless other worlds. It transforms Venus from a cautionary tale about our own planet's future into a vital Rosetta Stone, the one example we have to read the hidden stories of climates across the galaxy. This brings us to the final and most profound mystery of all. Is the endless hurricane of Venus a bizarre fluke, a one-in-a-billion cosmic accident, or is it a common, even inevitable, fate for worlds like our own? The answer defines how we see not just our neighbor, but every rocky planet in the galaxy. If a thick atmosphere on an Earth-sized world naturally develops this furious spin, then Venus is not an outlier. It is an archetype, a standard model for a class of planets. This shifts the super-rotation from a scientific curiosity to a fundamental planetary process, as important as volcanism or plate tectonics in shaping a world's destiny. The terrifying question then becomes, could Earth ever undergo such a transformation? Our planet possesses a thick atmosphere, and while our rapid rotation currently prevents a Venus-style thermal tide from taking hold, the underlying physics is universal. A runaway greenhouse effect triggered by a massive release of carbon dioxide could thicken our atmosphere and radically alter its circulation. While our strong magnetic field and lack of a global sulfuric acid cloud deck make an identical outcome unlikely, the principle remains. A planet's climate is a dynamic, interconnected system, and pushing one lever too hard can trigger cascading changes that shift the entire atmosphere into a new and hostile state, a state that might then become locked in for eons. The storm on Venus, therefore, is more than a warning. It is a lesson in planetary boundaries. It teaches us that an atmosphere can have stable states, and crossing a threshold can flip it from one world to another, from a blue marble to a yellow hurricane. Solving the 24 previous mysteries is not just about understanding another planet. It is about reading the only user manual we have for Earth-sized worlds, a manual that tells us which switches, once flipped, can unleash a fury from which there may be no return. The ultimate secret of Venus is not just how its sky moves, but what that movement says about the fragility and resilience of every world blessed with a blanket of air. Our journey through the 25 mysteries of Venus has revealed a world of profound complexity, where a global hurricane is powered by forces we are still struggling to name. From the hidden pulse of gravity waves to the enigmatic chemistry of its clouds, the super-rotation of Venus stands as one of the grandest and most humbling puzzles in all of planetary science. It consistently challenges our most advanced computer models, defies every attempt at a simple explanation, and serves as a powerful reminder that our so-called sister planet is a wild, utterly alien world with its own set of rules. The quest for understanding is far from over. The next generation of missions, with their sophisticated instruments and daring probes, promises to pry open the storm's deepest secrets, bringing us closer to a truth that is likely stranger than our current fiction. As we wait for those new discoveries, we are left to reflect on this astonishing atmospheric phenomenon. Which of these 25 mysteries captured your imagination the most? Was it the ghostly stationary waves, the planet-wide hunt for the unknown ultraviolet absorber, or the terrifying possibility of a permanent climate trap? Let me know your thoughts in the comments below. For more deep dives into the cosmos's greatest enigmas, be sure to like this video, subscribe to the channel, and hit the bell so you never miss a journey into the unknown.